Hi, everyone. I hope you're doing well. This is lesson 5, the last lesson of our first unit. In this lesson, we're going to talk about this thing that we kind of discussed a little bit last class, but didn't call it this, but it's called the rule of sum. And in this lesson, we'll look at that, but also kind of how we're combining a lot of the different concepts that we've learned to this point in different situations. Within that, we have one big one, which we've been using ever since lesson 1, really, which is the fundamental counting principle. And this is when you have more than one event. And really what you're doing with each event, you take the number of outcomes of each event and you just simply multiply them together. So for example, if I was to flip a coin 5 times and I wanted the number of outcomes I could get, then really that's 5 stages or 5 events. And I have 2 outcomes in each stage. And so it's really 2 times 2 times 2, 5 times. Today, when we're talking about the rule of sum, we're really looking at when you have one event, and the key word here is or another event occurs. And this is different, and we'll see. Sometimes it's obvious and sometimes it's not, but one key thing to look for to help you tip off is this idea of one thing or another. And we'll look at this example below to help illustrate that. So last class, we talked about this thing called mutually exclusive events. And what that means is that they just have no intersection. So no intersection is what mutually exclusive is. Another way to think of it is that these things cannot occur at the same time. And we'll look at a bunch of examples where they can't occur at the same time. And that tells you that they are mutually exclusive. So let's start with a really, really simple situation. It says, how many ways could you roll a 3 or a 5 with a 6-sided die? So 6-sided, got the numbers 1 through 6. If I think of this, and you could probably answer this question very quickly, but if I'm going to deliberately take my time with this. I have one set, which is the number of 3s, right? And so you think on a 6-sided die, there's 1 3. The other set is the number of 5s. Is there any overlap between these things? No. There's nothing in common. So I have my 3s and these are my 5s, but really there's just one of each. And I'm looking at those 2 sets added together. So I have 1 outcome plus 1 outcome for a total of 2 outcomes. This is mutually exclusive because they have nothing in common. The key here is that I'm combining the number of outcomes because it's saying the number of outcomes with the 3 or a 5. And this is technically the rule of sum, also known as the additive principle. So if I was to write this formula, which we saw last class, the number of A or B, knowing that they are mutually exclusive, it's really just the number of outcomes in A plus the number of outcomes in B. This is the same as saying the number of A union B. Same or union, same thing. Let's look at an example that involves what we already talked about once, but then I'm going to change the wording really slightly so that it looks like the rule of sum. So it says, how many license plates are possible if you have 4 letters and then 3 numbers? And we're going to assume that repetition is permitted. So we had this question earlier. That means I've got 1, 2, 3, 4 letters and then followed by 3 numbers. We can use all 26. We can repeat them. So this is all 26 multiplied together, and then this would be my times 10 3 times. So it really comes out to 26 to the exponent 4 times 10 to the exponent 3, and you would punch that in your calculator, and you get a really big number. This was the multiplication rule. This is the fundamental counting principle. We're multiplying each event, in this case character, the letters and numbers, with each other to get a really big number. If I change the wording ever so slightly in this second example here, it says, how many license plates are possible if you can have a plate made of either 4 letters, and here's the key word, or a plate made of 3 numbers? So let's imagine this for a second. This scenario means that some people have license plates that are just letters. For example, AAAA. That would be a license plate. Other people have license plates that are just numbers, 3 numbers in fact, so like 111. No one will have a mix of those, where the first example above, you have a mixture of all of them. in the order of letters and then numbers, but you can mix for each one of them. It's really a 7-character long thing. This is really going to be 4, and then separated, some people will have 3 numbers. Because it's one thing or the other, that means that I am adding these separately. Kind of like the example above with the number of 3s and the number of 5s. So this is 26 4 times, and this will be 10 3 times. And so again, I would punch this in, so that's 26 exponent 4 plus 10 to the exponent 3, and we get quite a bit smaller number, 457,976, like that. So really big important idea is that if you see and, you're almost always going to multiply. If you see or, you're going to be adding. Let's look at another example down here. It says at a round square conference, either 8, and again, or 9 countries' flags may attend. In how many different arrangements could the countries' flags be flown? So one thing to consider is that is there overlap in this? Can you have 8 flags and 9 flags at the same time? And the answer would be no. If they cannot occur at the same time, that's this stuff in purple at the top here. If they cannot occur at the same time, then you know that they're separate. It just doesn't make sense to have 8 and 9 at the same time. So if I was lining these flags up, this time we're talking about something with factorials. So the number of 8 countries lined up plus the number of 9. So I'm adding them together because it's one or the other. And if I line up 8 items, assuming I just have those 8 countries there, I really just have 8 factorial. If I had 20 countries to choose from, that would be a different question, but you would have 20 P8, and we'll get to something like that later. And then this one would be 9 factorial if there was 9 countries there. And it goes down like this 8 factorial, remember, is just 8 times 7 times 6, all the way to 1. It goes down because as soon as I use a country's flag, I'm not going to reuse it. I can't really reuse it unless I had duplicates, and so I would use somebody else's flag in the next one. Again, you can punch this into your calculator, you get 403,200, like that. Great. There will be more examples where you can kind of work your way through it in the homework questions for those. But let's tackle a few other things. So the second part here is, well, what if there is overlap? What if they are not mutually exclusive? And when I say not mutually exclusive, it means there is an intersection. And so a fancy way to explain this is that we use this idea of principle of inclusion and exclusion. I'm not going to really test you on that, but that really just means if you've double counted, you have to subtract the double counted part. And we saw this within the Venn diagrams last class. So if I say the number of A or B, which we've been talking about, I take the number of A plus the number of B, but I have to subtract what's the intersection is, which has been double counted. This is the same if I write the notation A union B is the number of A plus the number of B minus the intersection. And remember, the intersection is the upside down U symbol. So it really means everything that you can find within these two things, the two sets. A real easy example is to use cards. So for example, if I was to say, how many ways can you draw a face card or a heart? So I've got the representation here. I don't know if we talked about face cards, but these are my face cards, the Jack, Queen, Kings. So there's one of each in all of the suits. There are 4 suits, so my face cards. And there are 12 of them if you count those up. The other set here are hearts. So here are my hearts. And there are 13 hearts. Notice, however, there are some that fit into both categories. So these guys right here, there are 3 face cards that fit into both. So if I was to say to you, you're playing a game, and if you draw a face card or a heart, and you want to find out the number of ways you can win, then you don't want to double count those face cards, which are also hearts. So this is that idea where we have an intersection. So if I was to write this out kind of in the long way, I would have the number of face cards union hearts is the number of face cards plus the number of hearts, but then I would have to subtract the intersection of face cards and hearts. So if I do that, I've got face cards, there's 12, hearts, we said 13, and we've double counted 3. You could also represent this using a Venn diagram if you wanted and figure it out that way. The visual, I think, here is quite helpful to have that. That one's not too bad. It will start to get harder, especially when we get into more complex situations involving probability. So I think it's good to have a solid understanding of this now before we get to that. The next one, you can try this one. I don't think you need my help for it, but you can pause the video right now. I'll just lead you through it. It says, out of a group of friends, 18 have Netflix and 14 have Disney. If 7 friends have both, how many have at least one of the two services? That means you could have one or both. So again, you don't want to double count somebody. So we're going to use that little formula. And you don't always have to write out the notation. In this case, I've got the number of Netflix, let's say, N union Disney D. So I've got the number of Netflix plus the number of Disney minus the number of the intersection. And so I've got 18 plus 14 minus the 7. And we kind of did this last class, but we did it in a Venn diagram setting. And so if I add these two together, this would be 32. So 25 total would be my answer. Great. You'll have more examples of this going forward. But now I'm going to introduce another thing, where actually a couple more things we're going to do. But this is the rule of sum, but we are involving permutations. So it's something we talked about a couple classes ago. This example, determine the number of arrangements of 2 different colored balls, or, again, keyword, 3 different colored balls from a total box of balls of 5. So if I just said to you, how many ways can you arrange 2 different color balls from a total of 5? You have more items than what you're actually going to use. We have 5 items, but we're only going to use 2 of them. This fits into a permutation. That's the definition of a permutation, more items, and you're going to choose some of them. So you could write this out as 5p2, or you can think of it as you have 2 spots for the balls, and you're going to pull those 2 balls out. The first number of options for the first ball, or the first stage, you have 5 of them. You take one of them, assuming you're not going to put it back. The next one would be 4. This is going to be combined separately with 5p3. This one would be like having 1, 2, 3 choices, 5 for the first, 4 for the next, and then 3. So you end up with 20 plus 60, which gives you a total of 80 different options. This is, again, an example where these 2 things cannot occur at the same time. You can't have 2 and 3 different colored balls out of the 5 simultaneous. It just doesn't make any sense. So they can't occur at the same time. Again, you'll see a couple of examples in the homework like that one. The last one here, it kind of, we'll read through it, but it's going to kind of set you up for the part C, really. And so we're going to take our time to go through the first 2, which are really just review before we get to something new in the third part here, part C. So it says, let's say we have the digits 1 through 6. So we've got 6 total items. What's the total number of arrangements with no restrictions, assuming repetition is not permitted? And we'll write the notation for the situation, and you'll see why I want to do that in a second. So in this case, I've got 6 factorial because I've got 6 spots. So really it's just 6 factorial. And I believe that's 720, but let me just double check. Use my factorial button. Yeah, 720. And this, in this situation, and you'll see this sometimes written, with no restrictions. This no restrictions means that this is the universal set. And we're going to use that idea in a second here. But this is, remember, the universal set is all the possible outcomes. So the total possible outcomes or arrangements. Again, universal set. And that's going to become important for part C. Number 2, we've seen this question as well. It says, what are the number of arrangements if these two numbers 1 and 2 must be beside each other? So if I put 6 spots, remember we said it's like these two numbers become 1. And so instead of having an arrangement of 6 factorial, it now becomes like I have 5 items instead of the 6, because the two numbers 1 and 2 are acting like one unit. And then because I can switch those two numbers, instead of 1 and then 2, it could be 2 and then 1. I really have this times 2, and technically it is 2 times 1, or 2 factorial, so I'll write that in. So this becomes 5 factorial times 2, which becomes 240. So that's good. Hopefully you remember that part. That's a bit tricky. I think we did that in lesson 2 or 3. The last part here is going to add one other thing to this. It says, what are the number of arrangements if the numbers 1 and 2 must not be together? So they're not allowed to be beside each other. And I've led you through this for a specific reason to see these parts A and part B. But let's just think about this for a second. So imagine you had 6 spots. If I start to try to think about where the 1 and 2 can go, imagining they can't be together. So I could have the 1 here, I could have the 2 here, I could have it here, I could have it here, I could have it here. Or I could have the 1 here, and I should say I could switch these two. And you don't have to keep up with me here because I'm just trying to prove a point. If I put the 1 there, then that means I could put the 2 here and the 2 here. Oh yeah, and I can switch these two. I could try to figure out all of these different situations. If I put the 1 there, I could have the 2 there, I could have it there, I could have it there. So it's like, it's obviously really hard to figure that out. And it would be, you probably could do it, but it would take a long, long time. And it's not very concise. And if I had, let's say, 50 numbers, it just would be impossible. It would take forever. So what I'm going to do is I'm going to do this a different way. And often if you try to solve something directly and it's like, wow, this just seems like too much, there's probably a better way to do it. Sometimes there isn't, but most of the time there is. And it has to do with this idea of this situation being the complement. This is the opposite of part B, where they must be beside each other. And this idea of the number of A plus the number of everything that A is not, we talked about this, is equal to the total number of all of the options, or the universal set in that situation. So if I describe A, let's say A is the number of ways where they must be together. So I'll just say together. Then the opposite of that, or the complement, is the number where they're not together. And if you think about it, that actually takes up all of the possible outcomes. Those are the opposite to each other. And if you're not in set A, then you must be in the opposite of set A, A prime. And all of that equals the total number of all of the possibilities. This thing can be rearranged because we want to find the number not together. I can simply take the universal set, the number of S, and subtract the number where they are together. That becomes a lot more manageable than what I was showing on the side here. So we said the number where they are together is 6 factorial. The total number of all of arrangements is 6 factorial. The number where they are together is 5 factorial times 2. And so it's really this minus what we got above, 240. And so I end up with 480, I believe. That's the number of options where they are not together. And this idea of the complement, it's tricky to really wrap your head around sometimes, but it becomes really essential in trying to figure out some complex problems, somewhat like this one, and often problems where there's many different outcomes. Okay, hopefully that's helpful. You can try these questions down at the bottom. Remember, full solutions are available in the content library. See you later. Bye-bye.